So it's great to be here. I haven't been in a couple of years, actually. I was here a little more regularly in the past and gave a talk a couple of times, so it's great to be back. And what I'd like to tell you about today is some work that we've done as part of a broader context. And I felt confident enough to have sort of a rather grandiose title, sort of why deep learning works. So there's two reasons for that. One is I think we have an answer that I'll describe, but also two, we're even asking the question. And that's not a question most people ask, right? Most people that do deep learning algorithms think of it from a very engineering perspective, and their goal is just to get better training or test or something. And they don't ask sort of the why question. Build it and break it fast and whatever, but they don't ask sort of why it works. And so if you don't ask why it works and you sort of put Band-Aids on Band-Aids on Band-Aids, it can get hard to unravel what's actually going on and try to understand why it actually works. So we're going to try and ask a why question. And in particular, at the heart of what we're going to do, we're going to ask certain scientific questions. And we're going to have a methodology where we can essentially have a control, a validation to answer the why question, which is typically not done. What's typically done is you train this thing to death and you push into production. If you're at a university, you run an algorithm, you do something the night before, you scramble before a deadline, and you push it out the door, and then you move on to something else. So we're going to try and break it, and we're going to try and have a control to say why it works. And let me shift over to the other slide deck. So this is going to be work that's largely joined with Charles Martin. So Charles is someone I bumped into a few years ago. He runs a boutique consulting shop, calculation consulting up in San Francisco that does consulting for a wide range of machine learning and AI and that sort of problems. So this is going to be joint with him. And I bumped into him at one of these meetings some number of years ago, and we got to talking about this, and he was saying this whole neural network thing's sort of crazy, right? People are doing this stuff, they don't have the foggiest idea why it works. On the academic side, it violates just very basic assumptions about statistical learning theory and stochastic optimization. On the applied side, it works, and then it doesn't work, and it's hard to understand what's going on. And so we sort of tried to answer the question why it works. So there's going to be a couple of perspectives here. So one, I come at it, I don't have a dog in this fight, right? I mean, I don't think of it in terms of computer vision or NLP per se. We're thinking about it in terms of foundations of algorithms. I did work on randomized linear algebra, and you'll see some of those ideas floating around. You actually need surprising little random matrix theory for that, but we'll see that here. I'm involved at Berkeley with a range of things and sort of foundations of data science or theory of data. So we're going to be asking sort of very foundational questions, and there's going to be some heavy-duty theory we bring to bear here, but we're going to try and have a very practical theory, and I think that's also different than a lot of the machine learning theory, where there's really a fairly strong disconnect between the theory and the practice. So we really want a practical theory for deep learning. And then there's a range of phenomena that people make a big deal about that just don't make any sense, and so I'll talk about one that is a so-called generalization gap, which has to do with when you train at large batch sizes, things do less well. And I'll describe how it's a very natural sort of side effect. We make very particular predictions, and we'll see what we see.
Someone who knows more and more about less and less demonstrates the generalization gap.
Maybe so. It's hard to argue with that. And so we're going to try and also engineer better algorithms here. So we'll talk about what that may mean. So background. So one on the theory side, convex and not convex optimization. Convex theory says one thing. These algorithms perform completely different. Statistical learning theory says one thing. These algorithms perform completely different. So in that sense, it's a nice playground to sort of think through ideas on sort of foundations of data. What is regularization? What is it, right? I mean, some people say it's a Bayesian thing. Some people say you have a regularization parameter that you cross-validate. Maybe it's every knob you fiddle with. So what actually is it? Is deeper better? There's lots of papers that say deeper is better because it gives you more knobs to fiddle with, and so deeper must be better, right? Because it's like the brain or something. So is it better, and why is it better, or why is it not better? And we want to use these insights to get practical insights. So maybe ask the question, when is your network fully optimized, right? Can you ask the question, when should I stop training? Right? People usually train until they just get tired and then stop. Is that a good MO? Can you have metrics that allow you to do that? If you're a small player, not Google or Facebook, but you run a consulting shop, you run a small company, you take a publicly available network and you tweak it a little bit and you add another couple layers and you optimize that. You don't have a lot of data. You don't want to peek at your data a lot because you might corrupt it. Can I ask the question, can I look at the structure of the model and answer the question, is this well trained or not? Or I am at a big company, and I'm not going to share with you my data, and I push my network out the door for you to fiddle with. Maybe I'm an adversary, and I just push garbage out at you. Could you answer the question, was this network trained to good data, or was this network trained to garbage? So we'll have partial answers to some of these, but this is the sort of practical theory we want to be talking about, in addition to things like large batch sizes versus smaller batch sizes and so on. So the motivation here came from a particular paper on the top left. If you know the area, maybe you've seen that. If not, this is one of many papers that just says, see, here's a plot, and we're going to make some extreme hypothesis and derive some stuff. And this particular one had to do with a so-called spin glass structure of the energy landscape. And if you really look at this, the leap to spin glasses was completely unjustified. I mean, you can get away with much more modest hypotheses as to what might be causing this. And we saw down on the bottom left, I'm not going to describe what the x and y axes are, but something that's very structurally similar. And this has to do with sort of the number of states as a function of penalty. You know, is there a large number of states or a small number of states above the minimum in systems that are not spin glass? And if you don't know, spin glass is good. I mean, don't worry about it. It's a very complicated and esoteric object. And it'll be sort of relevant to what we'll talk about, but the main point is that you want to stay away from them. So on the bottom left, you have a much more modest hypothesis as to what's going on. And so we said what's really sort of striking us here is that on the top right, people have this idea that there's some sort of landscape of the objective, right? If you're a convex objective, that you're a nice bowl, like a quadratic function. And then maybe you're not perfectly quadratic, it stretches out more on one side or another. But the idea of essentially a convex function is you can call a black box, and any well-engineered black box will find the minimum, you know, subject to it. Not convex is everything else, and it's, you know, the Wild West. And you know, in spite of that fact, these things perform well. You tend to find similar solutions of similar quality. So how can that possibly be? And so this is going to raise a range of sort of broad questions that we wanted to address. So the approach you want to take, so roughly, you know, the energy landscape that I just referred to, there's an object we'll get back to. This sort of is essentially the structure of the penalty, or the loss, sometimes it's called. It's called energy because it has formal similarities with physics, but it's the loss. And so let's say your loss is E, and it's, you know, it's a weight matrix. You have some biases. You filter it through some sort of sigmoid or something else, and you iterate this 10 times, or however many, you know, 500 times, depending on how deep your model is. And what you do, you train this on labeled data. It's natural languages, it's images that are labeled in terms of cats and dogs or whatever. And this energy is the energy landscape. It's the part of the optimization problem, let's say, that's parameterized by unknown elements of the weight matrices and bias vectors. And the idea is that you pass the data through this, you look at the errors, and you propagate those errors back, and you do that iteratively. And there's a gazillion parameters, and you fiddle with all the parameters at every step. And this is very, very different than, you know, ridge regression, where I have an F, I have a G, it's least squares, it's ridge, or, you know, L1 or L2, and you say F plus lambda G, which is the way people in the past have sort of implemented regularization. So this is a very different structure. And so, you know, the energy landscape may be changing at every epoch because the structure of the surface may be changing. And that's actually very different than you'd see in a lot of sort of traditional machine learning models. So what you'd expect is that, and when I say what you'd expect is what the machine learning or neural network community expected in 1990 was that the surface would look like on the left. Wildly non-convex, whatever that means. You're in a million dimensions, who knows what's going to happen. And so, you know, look at papers in 1992, they'd say these things, we expect lots of local minima, and maybe, you know, we're not exploring the full possibility of this model because we get stuck in a bunch of local minima. That's 1992. 1996, empirical fact, minima are never a problem. Why? We don't know why, but they're just never a problem. And so, you know, you look convex, in fact. And so by 2000 or 2001, this is well enough known that it got into textbooks. I mean, so this is just, in low dimensions, you draw a picture. In one dimension, you see a bunch of minima. High dimensions, that's just not an issue. If you're in a million dimensions, that's just not an issue. So how can that be? What's going on here? A related thing has to do with what counts as regularization. So regularization is this phenomena, basically, that I don't want to overfit today's data. I want to be a little bit robust so that I fit to tomorrow's data. Don't want to fit to the peculiarities of today's data. And if I have ridge regression or regularized SVM or anything like that, I have an objective, I have a loss term, I toggle between the two with some additive term, and I cross-validate, or I choose the lambda parameter somehow. Lambda is your regularization parameter. It says that, you know, the struggle between the objective you want to optimize and sort of how rich the model class is. The problem here is that what is regularization? So as part of this, you feed data through the network, you back propagate, you may drop out some entries just sort of randomly here and there. You may do early stopping, right? I don't want a million steps of my iterative method. I run 5 or 10 or just until I get tired of running it. Maybe I have batch size. Inside my stochastic optimization algorithm, do I choose my batch size to be 10 or 100 or whatever? Big difference, it turns out. Noisify the data. I might add noise to the data, randomly or adversarially or in a range of different ways. Every one of these things is regularization or has a regularization effect. So if everything is regularization, you've really emasculated the term of its meaning. Nothing's regularization, right? So what does it even mean to be regularization? So this sort of struck us because the best paper award in ICLR is the top venue in neural networks. The best paper award, not some random paper again, the best paper award was given to a paper that said, more or less, large neural networks can easily overfit and overtrain data, and popular ways to regularize may or may not help. Understanding deep learning requires rethinking generalization. And we thought this was a little strange because, in fact, this was known 20 years ago, and so we wrote up something. Rethinking generalization requires just revisiting old ideas. Not VC capacity theory as it's parametrized in theoretical computer science and mathematical statistics and VC theory. A very different approach, so the statistical mechanical approach, which looks for typical case complexity, will explain these and a whole bunch of other sorts of phenomena. That's the good thing. So this was we got to know each other. We said, why don't we do this? And this is sort of what's going on. That's the good thing. The bad thing is it's extremely technically complex. You need to love statistical mechanics to know or do it, and it's certainly not something you can just hand off in a data science boot camp in an afternoon or something and give to someone, right? Which is, it takes 5 years or 10 years to learn statistical mechanics, right? It takes an afternoon and a half to learn data science if you can get your Python compiler. So it's a very different mindset in terms of what it means to mean something. So, so we wanted to operationalize this in some way. So what I want to talk about is a theory to operationalize it, and then some of the sort of practical consequences we've seen in some forward-looking directions. So regularization, think of ridge regression. F plus lambda g. And that's the same as lasso. It's F plus lambda g. And that's the same as a ridge regularized SVM, F plus lambda g, right? The F and the G differ. They may depend on the data or not. But the idea is you have a scale. The scale is defined by lambda. And think of ridge regression, right? Above that scale, signal. Below that scale is noise. It might not be noise, but you're thinking of it as noise. So you cut a scale. Above is signal, below is noise. And so you can formally relate that to early stopping and iterated random walks and so on. People have sort of made those connections. But this is one way to think about it. How are we going to think about it? We're going to think about it the following way. What if you didn't know if I'm optimizing F plus lambda g? You don't know what I'm optimizing. I'm just code. I'm not going to show you what I'm doing. Could you, if you send me inputs, I return to you an answer that my code's computing. Could you figure out what I'm doing? Right, so if you give me lots of vectors and I always return for you a sparse regression solution, you might say, oh, you're doing lasso instead of ridge regression because that gives you a sparsity encouraging penalty. Or if I give you something that's pretty smooth, you might say, oh, you're doing ridge regression or something. So could you, by poking me, come up with a posteriori statistic to characterize what I'm doing? Then I open my code and you say, oh, it's calling, L1 regularized L2 in Python, or it's calling whatever. Oh, you're right. Of course, you may open up my code and it's a mess, and it's just spaghetti code, and then I clip here, and I truncate there, and I early stop there, and I do this and that. You can tell me what I'm doing, right? Maybe I don't even know what I'm doing. You can tell me what I'm doing because you're able to characterize with an a posteriori metric. So we're going to do that. So different types of regularization are going to leave different norms, in particular we'll talk about today, but more generally, and empirical signatures on the weight matrices. The weight matrices are the solution vector if you're doing regular, least squares. It's essentially the structure of the solution. So to the extent possible, we're going to turn off all regularization. That's easier said than done because everything's regularization, but I'll talk in more detail offline if anyone cares. We're going to turn it all off, and then we're going to systematically add it back on. We're going to study empirical properties of what's going on, and if it walks like a duck and if it talks like a duck, we're going to say it's a duck. And so what you should be thinking of is how can we justify a figure like this, where essentially the penalty surface is convex or quasi-convex or something like that if you want to get a little bit fancy. But it's not this wildly pathological non-convex. Now you have a little bumps there. But remember, I have a million knobs to fiddle with, batch size and learning rate and so on, so I can easily add noise to smooth out those bumps. But it looks ruggedly convex. And so in particular, what are properties of layer weight matrices that might give you this? Because this is what people see. All right. What happens to layer weight matrices? So don't evaluate your method on one data set or 2 or 3, evaluate it on 50. Because the exception proves the rule, and if you evaluate it on 1, you're probably looking at the exception. So we evaluated on 50, and since then a lot more. The initial ones I'll talk about. Look at some toy thing, Lenet-5 on MNIST, as a sanity check, but also to be backward compatible. look at a 3-layer, multi-layer perceptron, look at miniature version of Alexnet that we can train and retrain. Look at Alexnet Inception, and we've done 10,000 weight matrices across 50 or 60 different types of networks. So, okay, hello world. 3-layer MLP, 1, 2, 3. Fully connected, sort of as simple as you can get. What do you get? So this is a total straw man, but in data mining, lots of times people look at the SVD and say, how quickly does the spectrum decay? This is how it, I guess the next slide is going to be the spectrum. X-axis here is training epochs, y-axis is on the left an entropy of the eigenvalues, on the right is the stable rank, which is a robust notion of rank. It's a soft version of rank. So both of these go down. Now, if your eyes are good, you see that the entropy goes from 0.91 to 0.90. Is that a big thing, or is that real, or does that matter? The stable rank for FC1 in blue and an FC2 in green decreases, more significantly. So what's going on here? Is this interesting? So now you look at a scree plot, which again is a total straw man, and you see it goes down and to the right. So this says nothing. I mean, you're looking at the data through a lens that tells you very, very little about what's going on. But the entropy thing struck our attention because we would expect some interesting entropy properties to go on if you're squeezing out correlations as part of the training process. So then we looked at it on the left. We're looking at what's called the empirical spectral density. So we're taking weight matrices, we're slicing them. We're looking at the eigenvalue structure of that. All right, and the idea is, if you're familiar with latent semantic indexing or something, this should tell you a lot of information about what's going on under the hood. And the red is at the beginning of training. If you know anything about random matrix theory, Wigner's semicircle law and quarter circle law and so on, this is what that is, red. Now, why is there some deep significance to the fact that at the beginning of training we're a random matrix? Or does it simply say that people start training with random matrices? So this is a sanity check. At the end of training, we're blue, and we have the same bulk, we have a spike of a few things that stick out. And so if you know random matrix theory, this should make you fall off your chair and get pretty excited. Because what we're doing is squeezing out some bits of information from the bulk into a spike. Now, of course, there we're looking at singular values, on the right we're looking at eigenvalues, which is actually the first thing we looked at, which doesn't tell you anything. So you've got to look at these things through the right lens. And when we saw that, it was very clear, for reasons I'm not going to sort of get into, that this was very, very significant. So then we drilled down on this. And this is not complicated. This is 3 lines of code. So pull out a layer weight matrix, compute and these are 500 by 500 matrices. These are not, we did implementations in Spark of terabyte scale PCA, right? This is 3 lines of code. So this is not hard. During training, you get a bulk. The y-axis is significant because the bulk goes up to 2.5. After about 4 epochs, you get a spike at 3. After about 40 epochs, you get a spike at 4. So it pulls out a little bit. You're squeezing out more correlations, but there's a diminishing return effect. So what's going on here is that the entropy decrease we saw before is because the bulk barely changed and something pulled out of the spike. So this is on a 3-layer MLP. I don't know if I have it in this deck, but say that I trained, I guess I do have it later, Lenet-5 to MNIST or something. MNIST, you get 99.8. If you're anything less than that, you're not state of the art. So say that I take the spike out, which we'll see that we have this later, and I look at the bulk, and I zero it all out, or I make it random or something. I forget the number, 95% prediction quality. So it's 95% good on MNIST. So people are saying, someone's saying no. Anyone want to say yes? It's 95% good on MNIST. So it's not 99.8.
Somewhere between mediocre and 4.
It's a lot better than 10. It's 85 better than 10. It's only 4.8 better than 99, worse than 99.8.
But there were a lot of methods that gave you 98.
There wasn't a lot of methods way back when. This is the first one out of the box. So it's a lot better than 10. It's a lot worse than 99.8. Of the 500 eigenvalues, if you pull out a half dozen, or whatever the number is that's in that spike, that gets you from 10 to 95. And it's the other 490 that gets you up to 99.8. So there's information buried there, but it's really a second order effect that you've got to squeeze out and takes a lot of effort. So this is the first sort of result we had along these lines. Now to drill down a little bit more, 3 slides on sort of random matrix theory, which is sort of a large and complicated topic. But roughly what's going on is the following. The sort of hello world of random matrix theory. So if you have a fair coin, you flip it 1,000 times, you get 500 plus or minus 20 heads. You wait the age of the universe, you'll never see 1,000 heads in a row, right? So the analogous sort of statement holds for random matrices. If you have a random matrix and you look at its eigenvalue properties, they have certain niceness properties. And so the hello world version of niceness is the Wigner semicircle law. that if I have a symmetric matrix, I'm going to get the semicircle. So there's two things going on here. One is you're going to get a semicircle in the limit, n goes to infinity. Two is that for finite n is 1,000, the size of your weight matrix, the fluctuations at the edge have a very particular structure known as Tracy-Widom. They're not Gaussian, they're Tracy-Widom. And so we're going to be interested in the bulk, and we're going to be interested in the edge. And if we're looking at a fixed number of weight matrices, you're nowhere near a limit. So you have to be very careful about those sort of details. If you're not rectangular, you get something called random matrix theory 102, Marchenko-Pasteur. Think of this as Wigner. So any sort of random variables that are sort of nice, we want to deal with heavy tails that are not nice, but any sort of random variables that are in the Gaussian universality class, for Marchenko-Pasteur, you get something like Wigner semicircle. So the shape of those, it depends on the aspect ratio, it depends on the variance scale, it depends on a few other things, but you get a nice function that's very well characterized with a very clean bulk and edge fluctuations that are the same, Tracy-Widom edge fluctuations. So the vast majority of work here is done on this. Empirical question, is this at all relevant? Do weight matrices, aside from the initial step because they were designed that way, look at all like this? And the answer is no. So that's not obvious, but if you go look at it, the answer is no. So we'll get to that. 103 is heavy-tailed, and there's a lot of information in this chart that I'm not going to go through. The point is that if you have random matrices with elements that are heavy-tailed, by heavy-tailed I mean they're not Gaussian. They're not plus minus one. They're not nice. They're not the sort of thing that you'd get in a textbook that for Chernoff or law of large numbers or any of the stuff you know would apply. The tails decay much more slowly, and so the variance, the third moment, other moments don't exist. And so there's three characteristic regimes for the power law parameters, let's say between 0 and 2 and 2 to 4 and 4 and above. And in the same way as anything that looks roughly Gaussian will behave like a Gaussian in the limit. That's called Gaussian universality. These heavy-tailed matrices have a certain type of universality that are very robust to some of the details of their properties. And that's something we're actually going to be taking advantage of. So it's a lot worse than the Gaussian properties, but it's the way the data are. So you got to deal with that. Fitting heavy-tailed distributions, very complicated. Non-negligible finite size effects, lots and lots of details that I'm going to gloss over. So empirical results. So we'll apply it on a few small things, but the idea here is we want to apply it on pre-trained models. Why? I mean, everyone likes to train, so if you're training's hard. So we didn't want to spend mental cycles on training. We wanted to work on pre-trained models so we could spend mental cycles on this and figure out what's going on. So we're going to work on existing models. There's pluses and minuses to this. This is a little like running a drug trial, and you only get to talk to the people who survived. Right? No one publishes bad models at universities, at companies, anywhere, right? So we're only looking at good models. Now we can look at good models in a parameterized family as they evolved over time and say the early ones are bad or not as good. But there's this selection bias in what we're going to be looking at. But we're going to be looking at older things like Lenet-5, Alexnet, GoogleNet, VGG series, ResNet series, a range of other things. Table of numbers. Okay. Lenet-5. So this is characteristic of, this is a state-of-the-art model 23 or whatever years ago, 20 some number of years ago, right? So people can poo-poo this now, but this really can classify digits on envelopes better than people, right? So what you see is the following. You get a bulk, and you get a bunch of stuff sticking out. The red is the best fit we could do. There's a whole bunch of questions. Some of this is automated, a lot of it's not. So some of these best fits are eyeballs. Open question, do this in an automated way. So the bulks fit very well. And if you zoom in on the x-axis, you see there's a reasonably sharp edge near about 3.5. There's a little bit of stuff out, and there's some fluctuations at 4 or 5, and they go up a little bit larger. If you're a statistician, this is a spiked covariance model. This is consistent with the hypothesis of a spiked covariance model, a bulk plus spikes sticking out. And if you cut off the bulk, you're going to get 95% quality on your digit prediction by keeping just the top half dozen or whatever number of eigenvectors that is. Okay, so there's signal, and there's stuff that has a bit of signal buried into it, but it's very hard to see with this global lens. The fact that there's eigenvectors sticking out is a sign of regularization, an a posteriori metric of regularization. Right? I can say this is large, that's small. I can quantify it in terms of norms. There's a range of ways to quantify it, but the fact there's a bunch of stuff that's big and good and a bunch of stuff that's small and consists with noise is a empirical sort of signature of regularization. So that's old stuff. Look at Alexnet, and essentially anything after Alexnet looks this way. So we've looked at thousands of things. That doesn't mean everything looks this way. This means 95% of things look this way, and there's a bunch of exceptions that proves the rule that we look at and try and understand. So, the vast, vast majority looks something like this. So look on the right. This is actually very, very poorly described by a random matrix. This is the best we could do, and it's poorly described because between, whatever, a half and 2, there's a lot of mass eaten out. This is just a histogram of eigenvalues. There's a lot of mass eaten out, and it bleeds out. There's not sort of a crisp edge. It bleeds out very strongly to much larger values, and it actually goes quite a bit above 4. So there's a lot of mass there that's being pulled out. So you can think of it like you're pulling more information from the spikes out of the bulk, but they don't have time to get up to the spikes, and so you're eating more out of the bulk. I don't know that that's the mechanism going on here, but you can think of it that way. If you look at this on log-log and semi-log plots, this is consistent with a power law spectrum on the eigenvalues, and we'll get back to what's the significance of that. But this is Alexnet. I could show you, dozens and dozens of other things that look this way. An exception is inception. So you pull out a couple, the fully collected layers in the middle. We've done this on convolutional layers and a couple things, but these initial results are going to be just fully connected layers. There's a dip there. So there's an envelope that is poorly described by Marchenko-Pasteur. Looks like it may be heavy-tailed, and then you have that dip in between. That's sort of, so if anyone knows the background on inception, I'd be interested in this. I did work on social graphs years ago, and anytime you see a big dip like that, it's just a signature that someone did something funny at some point. They just took data from 2 groups and put it together and didn't optimize something to death. So this suggests this really is under-optimized, and so there may be a couple pieces to inception that were put together not fully optimized. So that's the claim would make, and if anyone knows the backstory on that, I'd be interested in that. So this is an exception, an exception to that general rule. So here's, so what we did, understand what we did. We said we want to go look at pre-trained models. We're not going to train stuff here. So we went and looked at pre-trained models, 50, 100 of them. We computed a bunch of metrics. We saw that random matrix theory ideas describe this reasonably well. You need some exotic versions of random matrix theory in terms of heavy-tailed properties. So now we want to use this to construct a theory. And it's going to be a theory that's going to make certain predictions that we want to use in various ways. So let's try and come up with a theory for that. And by theory, I don't mean VC theory. I mean a predictive theory. VC theory is not a theory in that sense of the word, right? It's a bunch of theorems that say if you satisfy these conditions that I probably can't check in practice, then I'm going to get such and such results. We want a theory. You've got to go to a desert island. You've got to bring an equation with you. And if you don't make a good prediction, the cannibals are going to get you, right? So think of your feet are at the fire, and you want to come up with a good prediction. So what are you going to bring to the desert island? We want a practical theory that's going to make a prediction on trends in generalization quality or how you should adjust batch size or something like that. All right. The theory is going to be, it's a phenomenological theory that's going to be constructed in terms of what we'll call 5 plus 1. It's really 5, but there's a corner case on the bottom right called rank collapse. But it's really going to be 5 plus 1, call it phases of regularization, qualitatively different types of regularization that you can exhibit if you're thinking of the basal level of noise plus signal on top of it. And we're going to characterize it phenomenologically in terms of the bulk and in terms of the edge effects at the edge of the bulk. So top left, you're random-like. There may be information there, but you can't see it through this global lens of random matrix theory. Bleeding out. You're random-like, you have a bit of stuff at the edge. Maybe that's something pulling out. It's probably not just a fluctuational effect. It can be hard to tell in particular examples, but some sort of bleeding out. Bulk plus spikes is top right. You have a bulk, you have spikes that stick out a factor of 1.1 or a factor of 2. And think of this as sort of maybe signal, and the bulk is the noise. Bulk decay. You really start to eat out the properties of the bulk. It's not at all consistent with being Gaussian-type random noise. And you have a much stronger bleeding out in terms of being above a nominal edge. And the edge effect is sort of meaningless to try and define this edge. And heavy-tailed. So it's not obvious from here, but if you look at this on a semi-log or a log-log plot, some sort of heavy-tailed distribution. That's reasonably well fit by a power law distribution, let's say. I don't want to be dogmatic about it. It's a power law or something else, but reasonably well described by a heavy-tailed distribution. And so the claim is we're going to exhibit these 5 phases. If this is like regularization, everything is everything, it's going to be, we're not making a falsifiable claim. A prediction we could say is, can we exhibit all 5 phases? Not by changing a million knobs, because there's lots and lots of knobs, but by changing one knob, learning rate, batch size or dropout or anything, right? Here's more details on exactly how it would characterize those phases in terms of bulk effects and edge effects. And you see W rand, lambda max, Gaussian, norms of delta sig. I mean, these are the bulk and edge effects that I was talking about. So it's more or less what I described. All right, lots of technical details I don't want to gloss over. Tikhonov versus heavy-tailed. So bulk plus spikes. So this is the Lenet-5 we saw before. And this is ridge regression, structurally. There's a scale. The scale is defined by the edge of the bulk. Above that scale is signal, below that scale is noise. So that's spiked covariance model. And that's a convenient limit to deal with in mathematical statistics because you go to some limit and things concentrate. Smaller, older models are reasonably well described by this. This is a perturbative version of just Gaussian random matrix theory. Your Gaussian plus a few, one or two or a small number of low-rank perturbation. More interesting is sort of a heavy-tailed self-regularization. So a gap between the bulk edge and the spikes that stick out is one notion of regularity, but just the magnitude that things stick out, the total mass of things that stick out. There's a range of other metrics that are much more interesting because all of those metrics will be exhibited much more strongly when you have some sort of heavy-tailed property here. So the idea here is that the W, so W, remember, we're looking at the weight matrices, right? After training. You trained it, gave it to me. I don't know how you trained it. And it has empirical signatures that are going to be consistent with a self-regularization in the sense that I didn't put regularization on. You probably didn't know you did. You just had lots of knobs. But I'm interrogating the model you gave me, and it has low stable rank, a robust version of rank, a range of other metrics having to do with this. There's a bunch of eigen vector localization metrics, some other things that I'm not talking about here. So W is not a random matrix. It's whatever you gave me after training. It's a strongly correlated matrix. It encodes information that eyebrows are here, and eyes are here, and noses are here, and chins are here, and cats are over there. I mean, it encodes lots of information. They're not random matrices. What we're going to do is model these strongly correlated matrices by random matrices. So this is a conceptual shift. Usually you use random matrices from the Gaussian universality class to model noise. Right? I don't know what the noise is like. It's a lot of different types of noise. I can't control, but I think no one or two data points is extremely important. If you're worried about that, talk to robust regression. And so I'm going to model it with a Gaussian random matrix and then do something. We're doing something very different. We're modeling the strongly correlated signal with a random matrix, but not a Gaussian random matrix, a random matrix with a heavy tail distribution. And the different universality properties are going to be key for what's going on here. So we're going to model the strongly correlated systems by heavy-tailed self-regularization, and we're going to use known results from polymer theory and other areas that might exhibit strong correlations, and I'll get back to that towards the end. And large modern DNNs all exhibit this sort of heavy-tailed self-regularization, everything after 2013. So why? I don't know, but that's an empirical fact, basically. So a summary of what we think is going on is that there's no single scale threshold. It's not, except for old things like Lenet-5. There's not a nice scale above which is signal, below which is noise. You're having strong correlations on many size scales. There's no simple low-rank approximation, right? There might be 10 eigenvectors in this heavy-tailed thing that are most important, but they do not capture most of the information. So think of LSI if you had a heavy-tailed term document matrix or social network, right? Britney Spears and the famous people, have the most followers, but it's not like they, in aggregate, capture most of the information or most of the pairwise connections. You're going to get contributions from correlations on all scales, and it's very hard to treat this perturbatively. And so if you go and do Chernoff-type bounds, that's a perturbative approximation of an infinite limit. A lot of the structural theory, machine learning theory, is of that form, and this is something that you can't treat perturbatively. So large modern DNNs are going to exhibit this sort of heavy-tailed self-regularization. I'm talking in terms of the empirical eigenvalues. The eigenvalues that stick out tend to have localized eigenvectors. There's a range of other things, so it's not just this sort of one metric we're looking at. I should also say, I'm going to vary the batch size next, but I should also say, talk to me offline if you're interested in details. We have a 50-page paper, we have a short paper, there's lots of details. We didn't want to make the paper 500 pages, so we didn't put everything in it. We did, I think, extremely thorough due diligence on what you might expect are reasonable things. What if you did A? What if you did B? What if you did dropout? What if you had noise data? What if you do something else? So we checked all these things, and if you do more dropout, things get more regularized. You may damage the prediction quality. If you do this, things get less regularized. I mean, all the sort of things you'd expect. So I'm not going to show you exhibiting different phases with learning rates and step sizes and dropout. I mean, the sort of things you might expect. I want to talk about batch size, and I want to make a prediction here. And the prediction is basically going to be, that we're going to be able to control with a single parameter all 5 of these phases of prediction. I mean, that's a strong form of machine learning prediction. That's a strong form of prediction for a theory if we're able to exhibit all 5 phases, because it says we know that we're in a parameter regime, and not by in an ad hoc way changing lots of knobs. By changing a single knob, we can exhibit all 5 phases. And we looked at the batch size because I think years ago people thought, well, you know, step size and all these other things, you know, there's something special about them because they're inside the black box of convex optimization algorithms. Then it became, quote, obvious to everyone that they're regularization knobs de facto. People still have a sense that batch size is an endogenous regularization, sorry, is an endogenous computation parameter that's sort of holy in some way, and you shouldn't touch it because you use it for parallelization or some reason like that. And that may or may not be right. We'll look at that and see that that's not. But I think people still have the sense, and so we want to look at batch size in particular because there's been a lot of talk recently about the effect of batch size on prediction quality for machine learning algorithms. And the idea is batch size has to do with, I'm going to choose a small sample of data to compute a stochastic gradient estimate. And I have 1 million data points, but I choose a batch size of 100. And so I get an estimate of a gradient. It's a very noisy estimate. And so if I was doing convex optimization theory, if I was doing convex optimization practice, larger batch size is better, period. I just get a better estimate, and I just converge faster better. Exactly the opposites of that is going on here. And why? You should think of batch size as a temperature parameter. It's a parameter that injects a lot of variance. So empirically, it's a temperature parameter. And so you're sculpting an energy surface. So don't think of it in convex land. And I say that, and I think people are very wed to the idea that stochastic optimization theory and VC theory tells them something. But here, I mean, really, the empirical results are largely orthogonal to what the theory would predict. So we're going to run the batch size computations and ask what effect does this have, knowing that larger batch size leads to worse results. And we want to exhibit all 5 phases and try and understand what's going on. So varying the batch size. So we want to make predictions, and we're going to show that we can exhibit all 5 plus 1 phases of increasing implicit self-regularization. So we're going to just change one parameter. I'm not going to add more dropout. I'm not going to optimize to death the other parameters. You can criticize me and say, oh, but you didn't train this thing to death. Yeah, if I had varied all 50 other parameters, I could have pulled the prediction quality back up, but we're just changing one because we're asking a scientific question here, not an engineering question. We want to predict the existence of all 5 plus 1 phases and characterize their properties in terms of heavy-tailed random matrix theory. So we posited, just by looking at a few examples, that you're going to have these phases. Do they even exist? I mean, if you go to read papers on random matrix theory, it's not clear that that stuff says anything about practice, right? I mean, they're fairly theoretical and exotic, right? In fact, it's an extremely useful sort of area of applied math. It's applicable to a lot of things, including what's going on here. But it's not immediately obvious that these phases even exist, right? We looked at the structure of the theory, and we said, based on bulk effects and edge effects, we're going to predict 5 phases. So do they even exist? And can we exhibit them? So now we're going to look at basically a miniature version of Alexnet and retrain. This is the only place where we retrained. What we're going to see is large batch sizes. You're going to get worse generalization accuracy. And we're going to see decreasing implicit self-regularization. So the generalization gap, all else being equal, small batch sizes lead to more implicitly self-regularized models. Now, why might this be? There's a lot of work recently, people talking about why this might be. The way you should probably think about it is, if I construct a batch size of 1,000 or 1028, you know, that's a lot of data points. And it's going to be hard to pull out correlations that are in 3 or 4, a small number of the data points, right? Whereas if I want to pull out fine-scale correlations and my batch size is 4 or 8 or something much smaller, you know, it's very plausible that I can pull out those correlations. Now, it may be much more expensive to do that because I have to do it, whatever, 256 times if my batch size is 4 to get the same number of data points had I had a single large batch. So that's an important question. But leave that aside and ask the statistical, the inferential question. It's believable that I might be pulling out finer scale information if I go to smaller batch sizes. This is a funny plot to look at, and I haven't fixed the x and y axes. The x-axis is a batch size, but it's in log units and decreasing. So you have to turn your head a little bit upside down and backwards. So I have the stable rank and the MP soft rank for mini Alexnet, 2 of the layers on the top left. What that says is that as you go to larger batch sizes, the stable rank decreases. So I have log units and it's decreasing, but that's what's going on the left. So larger batch sizes are going to lead to more implicitly regularized model. It's a smaller stable rank. The quality, as you get to very small batch sizes, say the blue on the top right, the accuracy goes up to very close to 0.1. On the training and on the test, it also gets better. Down there is good, so it's getting better. Why there's the big gap? At large batch sizes, they're the same. If I go to something above 1,000, they're going to be the same. They're different when I get smaller because I haven't optimized all the other parameters to decrease the training test difference. So that's the generalization gap. And so what we're seeing is, had you not known what's going on, I could look at eigenvector localization metrics, I could look at a range of other things. I'm looking at here the prediction quality, and then 2, the stable rank and the MP soft rank, which has to do with the edge effect versus the largest eigenvalue. And both get more regularized as you get smaller batch sizes. So decreasing batch sizes leads to better results empirically, and the idea is it induces stronger correlations in the weight matrices. Smaller batch size, you're going to squeeze out more information. You're going to get stronger correlations in the weight matrices, and those are going to be modeled by the heavy tail random matrices. Larger batch size are going to lead to worse results. It's going to wash out the correlations. And so you're going to be less, you're going to be less fine in that sense. So let's now just change batch size. I just showed you the plot justifying the quality. Batch size 500, you look basically consistent with the hypothesis of random. 250, the same sort of thing. Get down to 100, you start to see a little bit of that decay near the edge of the bulk. And you can see where I got the pictures from before. It was actually from this. Batch size 32, there's a clear spike sticking out from the bulk. Batch size 16 is still bulk plus spike, bottom left. But you see that I'm starting to degrade the quality of the bulk, both in the bulk, but more prominently you see that at the edge, because the curvature of that's sort of, convex and not concave. Batch size 8, so when we originally did this, we went to batch size 16 and saw this, said, how low can you go? I mean, batch size 8, batch size 4. Batch size 4, it's much more prominent. Batch size 2, we couldn't even get a flit that was plausible. And if you look at this on log and semi-log scale, this is a heavy-tailed. So decreasing the batch size gives you stronger correlations and leads to a more implicitly regularized model. Why is it more implicitly regularized? Because these metrics tell you it is. I mean, I'm not being dogmatic that you should use this type of regularization or that type of regularization. We have these metrics and a bunch of others. And this is the a posteriori, essentially the definition of regularization, right? How far the maximum eigenvalue sticks out from the edge or from the bulk of the Frobenius mass, or there's a range of other sort of related metrics that we've looked at. So that's sort of roughly the idea. I wanted to talk about how you might apply this and use it. But so roughly the idea is that we want to understand sort of what's going on in the neural networks. We look at them, what we see is they look a little like random matrix results, but heavy-tailed random matrix results. We went back to random matrix theory books, we pulled stuff out, we said let's form a theory in terms of the bulk effects and the edge effects and a couple other things. And the theory was the 5+1 phases of learning, sort of a phenomenological theory that's going to look at empirical statistics of the data and then make predictions. The predictions are that if you have lower stable rank or lower MP soft rank or other metrics that are just very traditional, we didn't invent these, right? These are go to a machine learning meeting or go to something. Those are just textbook, right? A stable rank and bulk plus spike, the gap, these sort of things. So by the metrics that people use in the areas, what you see is that even without putting any regularization on these things, you get just the training process itself implements this regularization implicitly. One of the things that I said we did is due diligence and sanity check, looked at a range of things. The justification here is that we're looking at data and the training process engineers in strong correlations. And we're modeling those strong correlations with heavy-tailed random matrix theory. A prediction of that is, what if you randomize all the labels and all the pixels if you're looking at images or sentences or something? You'd expect that you might damage all the strong correlations. And this whole thing should fall apart, and that's going to be the case, right? So there's different ways to damage the data, and this might fall apart. So that's a way to check and be slightly less sensitive to the fact there's a real selection bias here in terms of the networks we can work with. So we do see that. Applying the theory. So I'm going to skip over a couple of the details on how to apply it. There's a lot of, we have some code up, but it's not something you can just press the big green button and things, you'll become, your boss will love you tomorrow. But, but we have code up, so this isn't vaporware. But it's non-trivial to apply. We looked at ImageNet, there's a whole bunch of things, Allen NLP, looking at 500 matrices over 50 architectures. Here's the power law fits, and they range, the vast, vast majority are in the 0 to 2 or the 2 to 4 regime. There's a few that go up 5, 6, and some fraction, 10% or something are larger than 4. By the time you get power law fits that are that large, for finite size effects and other reasons, I mean, it's probably not a particularly good model. So we're fitting to something that's not the most appropriate model. And there's a bunch of other technical issues in sort of doing the fits. So I don't want to claim that this particular power law is 12 as opposed to 11. I don't want to give any significance to that. The point is here that the vast majority are in this 2 to 4 regime, 2 to 4.5 maybe. And we looked at linear layers. There's a range of ways to cut up convolutional 2D layers, and we looked at that. The random matrix theory applies to matrices that naively pull out linear layers or do sort of obvious hacks to convolutional layers. Question, can you do something better? So, if I have a geometry in an image, can I smooth something in a smarter way? Here's a new matrix, apply the theory. So that's an obvious next step. We have ideas, but we haven't pushed out any results on those lines. Exceptions to lots of rules. BERT was a natural language model that was put up, I think it was about a year, I don't know if it was a year ago or relatively recently. This is like Inception. This is an exception. So whereas before the vast majority were in the 0 to 2 to 2 to 4 regime, here we see a whole bunch of stuff, 4 and up, 6 and up, and so on. We're less confident on the application of this to NLP, although we applied it to NLP and a range of other things. So there may be properties here that are going on that are a little bit different. Our results would suggest that this, partly because it has large exponents and partly because it displays rank collapse. That's that 5 plus 1 phase, that corner case I was mentioning. This has that, where there's some weight matrices where they really are rank deficient. And that's something you wouldn't expect from random matrix results. So that suggests that this is not fully optimized. Open question. Can you use metrics like we're looking at to train this, not to you just want to push it out the door, but maybe to have some confidence that you've trained it to an appropriate level of optimization. So a summary of what we have: applied random matrix theory, 5 plus 1 phases of training. Two things. I mean, as a conceptual point, it's interesting that the training process itself, when you apply it to good data, implicitly implements a regularization, even in the spiked covariance and Lenet-5, the old stuff. That's sort of why that works. Much more significant is that you don't have the scale separation and you have these heavy-tailed properties. And it's remarkably ubiquitous. That's sort of neat, I think. But who cares, right? If you like random matrix theory or something, you might find that interesting. But who cares more generally? So I want to give you two examples. One, how we can use this. And two, what might this say more generally about why these methods, deep learning, neural networks, and so on, work sort of as well as they do in the cases where they do. So I want to describe a little bit on each of those. So using the theory. So let's use it. So this is going to be a historical description. We came up with something. We did due diligence. We saw that there was something related. So I'm going to start with the something related and then describe our result. So how do you control generalization quality? So in theory, you control it with some capacity control metrics. So VC dimension is a standard example of that. That's a very coarse thing. And so something that's gotten sort of attention, I mean, years ago in other contexts, in terms of matrix completion or whatever. But recently, in terms of neural networks, is sort of weight norm regularization. So the idea is maybe I'm not low rank, which is the metrics we were looking at before, but maybe I'm, the norm of my matrix is not too large. And so that norm is a capacity control metric. And so you can say, well, what if so theorem under some VC-like assumptions and so on, then that I may or may not be able to check. I'm going to get good generalization if I satisfy all these conditions. So there's a bunch of theory of that form. There was actually something by Lau and Poggio and Hidari where they used these ideas. They had to modify the network architecture and do a bunch of other stuff to make surprisingly good predictions on bounds for generalization quality for very small networks. So we're going to ask a different question, but we want to look at weight norms. If you look at, in particular, the product norm, I have a bunch of layers, pull them out, and take the product of the norms. That was something people did. You take a log, the log becomes a sum, so it's the average of the log. So it's the average of the norms of the weight matrices in log units. So is this going to perform at all? So people have proved results about bounds of generalization quality. What you see is that this actually does remarkably well to predict pre-trained networks. So here we have a VGG series, and the VGG series is a series where you can stick more layers in. So there's sort of a natural parameterization as the models become richer, better in some sense. And the test accuracy increases to the right. The log of the norms goes down to the right. And so you see a pretty strong correlation, actually. So we're going to be able to improve upon that, but pretty good results. So understand what we're doing. Someone, I don't know who, maybe someone here developed this model and pushed it out the door, right? We go. I don't know what data you used. I don't know how you did it. I don't know what knobs you fiddled with. I don't know any of that stuff. I'm going to look at the structure of this thing, and I'm going to measure some stuff, and I'm going to do some fancy eigenvalue stuff, and I'm going to come up with a number. That's the y-axis here. and I'm going to try and make a prediction on how good this is. And so we're predicting trends in generalization accuracy without even seeing the test data or the knobs that you're filled with. So not even seeing the test data. So you need to go to a desert island, and you want to come up with something that's going to predict, generalization quality. I mean, here's a metric. We'll give you a better one in a second. But here's a metric, and in most cases, you'll make a good prediction and survive the night, as it were, right? So we're predicting without even picking the test data. We're doing analysis of weight matrices. So I'm at a university, and I'm not at a marketing department. So I don't want to say I'm a marketer, but I can recognize a good name. And so we came up with a name. What are you going to call something if you're analyzing, looking at weight matrices and watching them? We didn't do it during the training process, but you could imagine watching weight matrices and using our theory to monitor training and saying when you should. So weight watchers. So if you go pip install weight watchers, you can actually reproduce these results. So this is interesting in terms of weight norms. What we wanted to do was to say the fact that there's this notion of, I'm using the word universality. I'm a little bit afraid to because it means different things to different people. So the notion here in math and statistics is you deal with random matrices because you don't want to depend on the details. In physics, it's a little bit different. It suggests that there's certain properties that are universal. And so I'm going to derive results in terms of random matrices because that's easier, but I'm really interested in the properties of the system that are maybe universal. And so what we're saying here is that, so I deal with, Gaussian noise, not because I think it's Gaussian, but because I know it's +1, -1, or whatever. But it's reasonably uncorrelated and reasonably independent. And if I have 1 million of those, it looks reasonably like a Gaussian distribution. And so that's what I mean by being universal. So we want to do universality here, but for the heavy-tailed properties. So the fact that we see such universality, in the sense of the word across weight matrices, suggests that the power law exponent might be a good metric. Because if you have a larger power law exponent, that spectrum is going to decay more slowly. You're going to have a largest eigenvalue that's going to be much larger, meaning the largest divided by the average or the typical value or the minimum is going to be much larger. And so this might be a good metric. Now just taking the average is not so good, so you come up with some sort of weighted average. So think of this as an unsupervised, we're not looking at data, right? It's unsupervised VC-like metric, but it's data dependent. And it's a complexity metric for predicting trends. We're not doing bounds, we're predicting trends in generalization accuracy. Because we're sitting on random matrix theory, which is trying to operational ideas from statistical mechanics. So we're not making worst case bounds that you do in theoretical computer science or statistics. We're trying to predict trends in the average case generalization because we want trends. So there'll be exceptions that either prove or disprove the rule. So what should the weights be? So in particular, we want some sort of relation between the Frobenius norm, which was used on the previous slide, and the power law exponent alpha. Okay? So look at a heavy-tailed random matrix. What we want to do is examine norm relations of the form Frobenius norm divided by lambda max. Lambda max is roughly the spectral norm. There's a scaling issue. But Frobenius norm divided by the spectral norm, think, by lambda max. But we're doing it in log units. And that's important. And how does that vary with alpha? So I'm not going to go into the details of why this is, but I'll wave my hands. I can talk offline. That alpha times log of lambda max should be something like the log of the Frobenius norm. So we're looking at real weight matrices. These are not random things. And so you could say, what's the source for the heavy tail here? One source for the heavy tail could be these are just random matrices. Another source could be this very strong correlations built in. And if I randomized all the elements, I'd screw that up, right? If these are just heavy-tailed random matrices, if I randomize all the elements, I don't mess that up. And so in mathematical finance, people do this all the time to test hypotheses about stock structure. And so we can do a similar sort of thing here. And so the alpha is going to be related to the log of the Frobenius norm, but it's modulated via the lambda max. And the idea is that the weights compensate in some sense for different size and scale of weight matrices, if you think of this as a feature map. And so what we get is this. So what we saw before, there's a bunch of things that stick down. So on the left is the VGG series. On the right is the ResNet series. So ResNet's another series where there's about a dozen different models. You can think of the old ones as, I don't want to say bad, but less good than the newer ones. And we see a strong trend here. We see this with test accuracy and top-to-one error and a bunch of different metrics. So again, we're predicting trends in generalization accuracy. So you come to me, I go to a desert island, you got to come to me and say, here's a model, tell me if it's good. And a theoretical answer to this is, well, what's the hypothesis on the data, and was it validated this? Tell me if it's good. or you're fired. Tell me if it's good or your paper's rejected. Tell me if it's good. I'll tell you if it's good. I'm only going to be right 95% of the time, right? There's 5% of the time we're not correct because we're only doing trends, but here's a metric, and we're not peeking at the test data or all the other million things that you did under the hood to, in terms of knob fiddling to get this to work. Again, you can pip install Weight Watcher to get this. All right. So there's a bunch of other things that I'm not going to talk about that are in the pipeline. So this is stuff that's sort of out the door. Use this to monitor training. We know of cases where this works. We know of cases where at least a naive application doesn't work. Is the theory completely wrong, or does it need to be refined? Because it's fairly exotic and it's taken a lot of sort of effort to get it here. Probably it's the latter, but prove me right or prove me wrong. So you could say I want to get finer scale information in terms of better matrices because I take into account the fact that there's an image and I've convolved something in some way. You could use this to monitor training. You could do this to say I want to have a more robust and interpretable model, right? You could be in a driving application. There you're willing to, you don't need to be 99.8. You're 50, 60 is good as long as you don't hit someone on the sidewalk, right? So you feed this into a system, and if you can understand what the model's doing, maybe it's good to not be heavy-tailed in that case, but to have a strong spike that sticks out because that gives you some sort of scale separation. I mean, I don't know. That's an open question. Can you characterize situations where you get a more interpretable model or something like that? So there's a bunch of things we're looking at. I can talk afterwards if anyone's interested. Let me talk a little bit at the end here in terms of sort of more general implications and what this might say about why sort of neural networks will work. So we originally started thinking about this because we were surprised that the machine learning community made a big deal about certain inabilities of natural control parameters, regularization knobs, to actually control anything, right? So the idea is, if you have a control parameter that you try and control a system and you muck about with it, something changes. But it may be the case that your control parameter saturates and you can't control anything. I mean, is that even possible? Of course. And so what people a couple of years ago observing in machine learning is that that's exactly the case. You have your usual regularization knob, and I can't control prediction quality. Why? Because you've saturated something. That's fine. And so we developed a very simple model which basically says you have lots of, if you add noise, if you do lots of other stuff, think of that like a load-like parameter. Back to the old days with an RBM. These are slightly different, but like a load-like parameter. And the stochasticity of SGD, the batch size, the learning rate, all these things, these are basically empirical temperature parameters. You don't have a formal structure of a statistical mechanical ensemble here, but what's batch size doing, batch normalization doing? Is this just rescaling something so you get sort of similar empirical estimates of the variance across scales? And so in a lot of cases, that's probably the case. And so if you go to basically any non-trivial model and view it through this lens, and this lens basically goes to something called the thermodynamic limit. So think if you have least squares, it's an n by p system. The theory is much easier if you fix p and let n diverge, or you fix n and let p diverge. It's much, much harder if n and p diverge together, because if you have two things diverging, the order of limits matters. So the thermodynamics limit's a little bit more like that. It's not fully general like that, but think of it, it's a harder limit to deal with. VC theory fixes this, lets this diverge. And that limit's going to go to a limit where you're just much too coarse to exhibit, to illustrate anything. So you get bounds, but in terms of prediction, I mean, you get results that are just qualitatively different than that. So any non-trivial model will exhibit a phase diagram, which looks something like this. So we talked about this. And so then the question is, if you're in a phase diagram and you saturate and you go to the wrong side of the phase, you will exhibit a spin glass type property. And spin glass roughly is you have a pathological non-convexity. So if you think of binary classifiers with n random labelings, you get something like 2 to the n over trained solutions. So the different wells here just will not talk to each other on the time scale of something exponential age of the universe. There's a lot of little local bumps in there, so it looks ruggedly convex in here, but globally, that's not the case. So empirical question, does the data look like this or not? And the answer, largely is no. It's going to look something like this. So can we justify this and understand this? So we took a page from actually where we came from, energy landscape theory. So where does energy landscape theory come from? It's been popular in the last few years in machine learning, but it comes from statistical mechanics and chemical physics. Here's an empirical fact that you may or may not know. Go to a biological laboratory, design a random heteropolymer. You have 20 amino acids, put them together in some random order, cool it down into some configuration. It'll be some blob. Warm it up. Cool it down to some configuration. It'll be some blob. Warm it up. Cool it. You will never get the same blob. Age of the universe, right? Now take a natural protein, something in your body that's been selected by evolution, cool it down, warm it up, cool it down, warm it up. You always fold to the same solution. If you know enough biology, yeah, there's an exception that proves the rule, but you always fold to the same solution. Why? Because you've engineered in correlations over many size scales. So that's been used to say you don't have the thing on the left, which is more like akin to a Gaussian type spin gas. You're going to get some sort of rugged structure, or sort of a rugged penalty landscape. And so what's a mechanism to get that? To have some random bulk and then a few good states, in a few good states that stick out, that have much lower energy or much better penalty or much better loss. If you have that, I'll wave hands here and sort of at the end. And instead of working with a spin glass model, we have Gaussian entries in an idealized setting, so Suzanne Bouchard says that if you have a spin glass with heavy-tailed entries, then the lingo is local minima do not concentrate near the ground state. It's not the case that if you look at the global minimum, there's something way over there that's epsilon better or worse. If you look at the global minimum, there's a bunch of stuff going on here, and there's nothing over there because you get this sort of rugged convexity. Now, this is theory that's very hard to talk about in terms of the way algorithms are parameterized in machine learning and stochastic optimization and statistical data analysis. So we had to come at it through this sort of very indirect route. And so, talk about this landscape funnel. If you train to noise, you probably damage this. If you train to signal, can you come up with mechanisms to get a better signal that gives you better rugged convexity? Is that what overparameterization is doing? So to conclude, a bunch of empirical facts, model in terms of signal and noise. We're going to model the strongly correlated signal in terms of heavy-tailed random matrix theory, and then use results from heavy-tailed random matrix theory, like that last result, to say that the long-range connections are going to short-circuit the pathological Gaussian non-convexities. Here, the states near the minimum are the only ones that are going to matter. You don't need to include all these other the way VC theory might. So you have a much smaller number of states that are going to contribute to the minimum. And in addition, you have so many knobs to fiddle with that this landscape really becomes essentially convex, ruggedly convex. We evaluated the theory in terms of the generalization gap. We made predictions in terms of predicting trends in generalization accuracies for state-of-the-art pre-trained models, and bunch of papers, bunch of code, bunch of stuff, and you can pip install Weight Watchers if I failed to mention that earlier. So with that, let me wrap up, and if there's any other questions or any questions, I'd be glad to answer them. So you can definitely design a neural network to have multiple local minima. That was the question. So you can definitely design neural nets to have multiple local minima, or some version of that. This has multiple local minima. This will have multiple global minima, up to epsilons. So there's a big difference here between local properties and global properties, and this I think is something that the area doesn't really appreciate. In a separate line of work, we were looking at great, faster optimization of large batch for second-order methods, so Hessian-based methods. People have noticed that if you look at gradients and Hessians, and we have results, you look at eigenvalues. If you do adversarial training, that flattens out the sharpness of the eigenvalues, and so that correlates with better results or something like that, right? Those are very local measures. If I'm running around here, I just have no idea what's going on there. So they cannot say anything about the global structure of the landscape. That's complementary to what we're talking about here. The ESDs take a very global view. It's a little like saying, if you have a one-dimensional probability distribution, you just look at it. It bumps up and down and put it on a piece of paper. If you have a million-dimensional, how do you characterize it? This is a little like taking a slice of it and looking at a couple moments. And so what we're saying is if you do that, and you know that you're close enough to a random matrix that you're going to model it by a heavy-tailed random matrix, you may be able to short-circuit these pathological non-convexities. So if you squint at it, it's going to look like that. Now, that's not to say if you don't squint at it, it's not going to look like that, right? So there's a big difference between, let's say, a zero temperature and a non-zero temperature. If you turn off all the stochasticity, yeah, you'll go here to local minimum, or there to local minimum, or there to local minimum. If you have a basal level of stochasticity, because the step size, because of dropout, because of any of these things, all those little bumps you'll sort of not see. You'll be optimizing an effective surface. And so that's a hard thing to quantify, to take this global view, but that's the way we're doing it here. And certainly, if you look myopically, then you're going to have lots of local minima. And so distinguishing those two, I think, is a tricky thing. But certainly, I don't want to say that there's no local minima, but as an empirical fact, that's not a problem for a practitioner. And sort of in a theoretical sense, yeah, there's local minima, but the large-scale structure looks like this. Because if you train and untrain and train and untrain, you always get to this same solution. I'll say that, but that's a little harder to quantify here. But certainly in the protein case, that's the case. But you get to a solution that bears sort of some structural similarities. So it's likely not the case until you get into that corner case where things saturate and you get into that spin glass corner where you get a situation where you have, you know, very different things that don't talk to each other.
Nowadays we're hearing a lot about AutoML. So would you say that AutoML kind of takes care of this variation, or the built-in all these, optimizing techniques with AutoML?
So does AutoML take care of all this?
Yeah.
I mean, the question is, does AutoML take care of all this? YouTube? The question is, does AutoML take care of all this?
He is repeating the question.
Repeat the question.
I'll repeat it for the 5th time. The question is, does AutoML take care of all this? You know, I don't know. If you're an engineer, probably, you know, just run it and it'll do okay. I mean, I don't know. So we're asking a why question. I think the question is, when, you know, AutoML is sort of shiny, and so what can be wrong with it, right? If a year from today you're coming back to me and saying, well, I did AutoML and it, you know, worked here, but then I hit a wall here and I have no idea what's going on, I'm going to still be looking at that and may have, you know, a 1 year more mature version of this talk. One of the uses you could do this is to say, you know, how does this feed into an AutoML system, right? Because if I want to look through parameter space, I mean, what am I doing? Am I going to do it blindly or naively if I'm going to understand some sort of structure here? I mean, can I use this to design a metric that says, you know, I'm going to have some sort of control on the rugged curvature or something? If I'm working on a smaller model and I want to scale up, or vice versa, I might have a large model and I want to condense it down. Do I want to look at just some naive statistic, or do I want to look at this? Or maybe a naive statistic is good enough, or do I want to look at this because this captures the correlations over many size scales? So if I want to put something on the cell phone, should I use it as a design principle to construct a much smaller model? I think all of these questions are open. So I think as an engineering question, this isn't going to do your AutoML thing for the next year. Right? This isn't going to beat that. Look ahead 2 steps. I mean, this sort of explains why it may work, and I think there's a question, how does this feed into very particular use cases like that, right? The predicting trends in generalization accuracy for these state-of-the-art models wasn't something we knew about 5 months ago, but was something we thought about. And this is actually one of the things that's also in the pipeline that we're looking at, how to feed to a range of things in that space, yeah.
When you were talking about eigenvalue characterization, when you were talking about eigenvalue characterization of the networks, how did you deal with different layers of the network? Were these particular weights of certain layers, or how you concatenated it? And if you looked at the difference of characteristics of different layers in this case?
So how do we choose the layers we're looking at? What are the properties if we choose different layers, et cetera?
Right. How did you deal with different layers?
You know, we wanted to get anything working, so we asked the easier questions first. So the first thing we were looking at, some of the earlier stuff, was fully connected layers or linear layers. More recently, we've looked at a range of convolutional things, in which case we unfold in sort of the obvious way, which I don't think is probably the best way, but you know, if it's A, I, J, K, L, you combine a few subscripts. I mean, so I think not the most stupid way. We're choosing, if you have a bunch of layers here, we're choosing things that are analyzable with random matrix theory. So if you have certain connections that short circuit that, it may not be a meaningful question to ask. Open question, how do you extend this to that? You know, I don't know.
Sorry, much simpler.
Yeah.
Let's take fully connected, 3 fully connected layers.
Yeah.
Each layer has its own weight matrix.
Yeah.
When you show like your slide, did you take matrices of all weights?
Yeah.
Of all layers, and did you compare those matrices?
Yeah. Short answer is yes. I mean, here I think I have it on this. top left, top middle, the FC1 and FC2 are fully connected 1 and fully connected 2. So we're actually looking at two different things there. A bunch of the earlier figures was similar. So pull out this layer, pull out that layer, do the analysis on each one separately. What do you get? We tend to see that towards later in the networks, these results are a little bit stronger. That's not always the case. So we looked at a layer. We didn't aggregate too much this way, except at the very end when we were taking that average of the power laws, because that would have homogenized too much information. We'd pull out a layer, would analyze it. Pull out a layer, different layer, analyze it. The question I was answering earlier was, pull out a convolution, will do this or that, analyze it. Yeah. So is that what you're asking? Okay. Yeah. Where was he?
Earlier you were mentioning the characterization of data dependent, not generalization guarantees, but kind of average case trend following. Could you maybe revisit how exactly you get data dependence in that characterization, as opposed to like when you see data independent? There's
two things there. What's data dependent and what's average versus not? So I think you're asking about this. The average versus not is VC theory, the form of a lot of statistical learning theories. If I satisfy these assumptions, then I get an inequality.
Right.
I'm better than this. That's not what we're doing. The structure of this theory just doesn't do that. This gives you typical case in some sense, but not naively typical. There's a range of ways to be naively typical. So that one aspect, to repeat, one aspect of the question might have been the bounds versus the trends, and that was the answer to that. The question I think you were asking was, I said something about this is a data-dependent VC-like metric. So VC theory says there's a range of ways to control capacity, and if you make certain assumptions on the input distributions, you can look at a VC-type entropy or an annealed entropy, and you can bound that with something, and you can bound that with something that doesn't depend at all on any assumptions, and this is the VC dimension. So this depends very weakly on the data, right? I mean, you don't need to know anything about it. You might expect, and it's the case, that you get very rough result. I mean, if your result applies to everything, I mean, that's a much weaker statement than if it applies to some things and not others. This depends on the data. So it depends on the data in a couple ways. The most obvious way is that I'll get a different number if I train to good data or to data that I added a bunch of random junk to. And the reason for that is that if I train to good data, I'll get whatever. I'll get a bulk plus spike. I'll get a power law with smaller values. Whereas if I train to noise, I won't get that. I'll get power law with larger values. I'll just get a bulk. I'll get something like that. And so as a function of the input data, I get more and less good models, more or less well-trained models. So the idea of the implicit self-regularization is even if you don't put regularization, I mean, whatever the knobs, you don't explicitly put anything in, the fact that you train to good data, and you do it with any reasonable set of knobs and parameters and hyperparameters, means that you'll engineer in something like a random bulk plus stuff. It's either spike or a heavy-tailed thing that sticks out. And that in and of itself is a form of regularity. But it's clearly data dependent. So is that what you answer what you're asking?
Would it be fair to characterize the fact the weight matrix itself exhibits other properties as being data dependent? So weight matrix depends on the training data. That's where the data dependence comes into this analysis?
So yeah, does the weight matrix, is that where the data dependence comes in? So we're not looking, so yes, so we're not looking at the architecture because we're pulling this layer out, pulling that layer. You could do that, and we've looked at that, but I didn't describe anything here. So pull this out, and the properties of this will be different depending on if you trained to reliable data or to noise or something, meaning the empirical statistics of this thing will be different. And so these alphas, the weighted alphas, these norms, all this stuff depends on the properties of this thing, and that will in general, depends strongly on the properties of the data.
So just a couple more questions, because we do have a drawing to do, and then I hope that you can spend some time just talking to people in the usual track. Any more questions?
There may be one over here.
Is there a question? Someone raising a hand or waving?
Very simple question. Sure, very simple question. You analyze weight matrices. Have you looked at embeddings?
Have we looked at embeddings? Yeah, we've looked at them. We don't have results on them. There's some properties that are similar, some are different. We were looking at this because we were trying to essentially capture the properties of the model. People have applied random matrix theory to a range of different things. I mean, properties of the Hessian as you iterate, embeddings, weight matrices. So we don't have any published results on that, but we've looked at that, yeah.
Okay, one more question. Do I see a question over here. Carl, I know you've been studying up on this, so.
No, I haven't. For your desert island tests that you had, when you were saying they were, you could see if they were good, isn't it really saying they're better than the other ones?
Yeah, so I said good, bad. I mean, it's more complicated than good, bad, yeah.
Well, I mean, you can't, there's no absolute value or a certain range you can set.
Yeah, I mean, we're looking here mostly at well-trained state-of-the-art. You probably could say good meaning sort of well above a random Besa level. So, you know, we could, it'll be the case that if you train to random noise and you do sort of some default stuff like that, you'll get something where, you know, you have a scale of the lambda max. And, you know, we could probably show that the numbers we compute are sort of statistically separate from that. So you could be better than that would be like using this for hypothesis testing or something. So we didn't do that because most of the things we were looking at were sort of well-trained state-of-the-art models, but you could imagine doing that. So question, is this a model I trained to signal a noise? So we didn't answer that partly because we didn't do the training and no one's pushed out bad models. But you could imagine using this and doing a hypothesis test and saying, am I statistically different than that threshold? So you could say, is it good versus just consistent with random?
So if you start zeroing them all, you know, near zero values, in theory they'll improve in one sense, but at some point you're going to cross the threshold.
Yeah.
Is there a way to kind of figure that out?
Yeah. So if you start zeroing out values, what effect does that have? Is that good or not? Not based on this. Based on other situations where we zeroed out elements of RBF kernels. And you could think of this as sort of a slice, meaning a feature map, but it was in a different context. Zeroing things out tends to add a lot of large-scale noise because you zero out according to some rule that's probably plausible, but not perfectly correlated with properties in the data. But you may enhance small-scale local signal. And I would guess that a similar sort of thing you'd see here, but we've thought about that, but we don't have results on that.
We have a request from the crowd what was the...
Also, it's going to be on YouTube right now, so if you want to go and see part of the talk.
So the question was about the URLs, this page. So an earlier version of these slides is up that doesn't have this page. I can put this version up in a day or two, and if I forget and you want it, email me. But I'll try and get this up in a day or two. These are all available on my webpage. And so if you go to my webpage, each of these 4 papers, as I mentioned at the beginning, is with Charles Martin. So if you search and if you do a search on, you know, Control F for find on the page for Martin, if you search for Mahoney, you'll get 100 papers. But if you search for Martin, you'll get just the ones that these are on. And they all came out in the last year or two. So you can do a search for Martin. And each thing's bulletized, and so the name will be there, the link to the paper. And if it's code, it'll just be linked to right there. So you can get that from my webpage also.